Right now, there's a spacecraft screaming through space at 430,000 miles per hour. At that speed, you could grab breakfast in New York and still make it to Los Angeles before your coffee gets cold. You could literally lap the entire planet Earth in less time than it takes to brew that coffee. Yet, here's the part that will absolutely wreck your brain. This same spacecraft, moving faster than anything humans have ever built, would still need over 6,000 years to reach our nearest neighbouring star. But hold on, because what we are about to tell you is going to flip everything you think you know about space travel completely upside down. Humanity's fastest achievement. Let's talk about the Parker Solar Probe, which is basically humanity's way of saying, "Hold my beer," to the cosmos. This magnificent piece of engineering holds the record as the fastest object humans have ever built. We're talking 430,000 miles per hour during its closest approaches to the Sun. To put that in perspective, imagine standing in New York. Blink twice. In those two blinks, the Parker Solar Probe has already passed Los Angeles, crossed the entire Pacific Ocean, and is approaching Hawaii. This achievement represents everything we've got. Decades of technological development, billions of dollars, thousands of the smartest people on Earth working together. The probe uses gravitational assists, basically stealing tiny amounts of energy from Venus every time it flies past. To really appreciate how fast this is, think about human history. For over 200,000 years, the fastest any human could travel was about 25 miles per hour on a galloping horse. By 1900, cars pushed past 60 miles per hour. The Wright brothers got their airplane up to 34 miles per hour in 1903. Within just 66 years, Apollo astronauts returning from the moon hit nearly 25,000 miles per hour. The Parker Solar Probe moves 17,000 times faster than those Apollo astronauts. And here's where the universe starts laughing at us. Even at this absolutely bonkers velocity, it would take approximately 6,600 years to reach Proxima Centauri, our nearest stellar neighbour, just 4.24 light-years away. If you started this journey when ancient Sumerians were figuring out how to write, you'd only now be pulling into the driveway. A human lifetime is roughly 80 years. Travelling continuously at the Parker Solar Probe's peak velocity for your entire life would carry you approximately 3 trillion miles. That equals roughly 0.05 light-years. The nearest star system sits more than 80 times farther away. You'd spend your entire existence travelling at record-breaking speeds and never even come close to leaving our stellar neighbourhood. The Oort cloud hammers this point home. This frozen shell of ancient comets marks the actual edge of our solar system. At humanity's current maximum speed, reaching even the inner edge would require approximately 600 years. An entire human lifetime at unprecedented velocities wouldn't even escape our solar system's gravitational sphere of influence. Consider Voyager 1 for a reality check. After more than 47 years of continuous journey, it has covered approximately 15 billion miles. That took nearly half a century. If the journey to Proxima Centauri were scaled down to a road trip from New York to Los Angeles, Voyager 1 would have travelled about 100 feet in 47 years. You'd still be standing in your driveway after half a century. Your neighbours would watch you age from youth to retirement while your car remained visible from their kitchen window. Light travels at 186,000 miles per second. Voyager 1, after nearly 5 decades, has covered a distance that light crosses in approximately 20 hours. The probe's 47-year journey equals less than 1 day of light travel. The rocket equation doesn't care about your dreams. The fundamental problem with getting anywhere in space comes down to a mathematical relationship so cruel it might as well have been designed by someone who really hates space exploration. Every rocket operates on the same basic principle that powered Chinese fireworks over 1,000 years ago. Hot gas goes out one end, vehicle goes the opposite direction. Simple, elegant, and absolutely devastating for interstellar travel. Chemical rockets face a mathematical executioner called the Tsiolkovsky rocket equation. For chemical propellants, exhaust velocities max out around 4.5 kilometers per second. This isn't an engineering limitation, it's a fundamental constraint imposed by chemistry itself. No amount of genius engineering can make water molecules exit faster than chemistry permits. Here's where it gets horrifying. To accelerate a small probe weighing just 1,000 kilograms to 1% of light speed using chemical rockets, you would need a starting fuel mass exceeding the total mass of the observable universe. Not Earth, not the Sun. Every galaxy, every star, every atom in the entire observable cosmos wouldn't provide enough chemical fuel. This is what the mathematics actually demand. So what about alternatives? Gravity assists allow spacecraft to steal energy from planets without burning fuel. But even a spacecraft optimized for gravity assists over decades might reach 150,000 miles per hour. Still hopelessly inadequate, still requiring tens of thousands of years to reach even the nearest stars. Ion propulsion systems increase exhaust velocity dramatically, but they produce thrust so minuscule their advantages evaporate for rapid acceleration. Hold a single sheet of paper flat on your palm. The weight pressing down equals roughly the thrust of an ion engine. Even with unlimited fuel and a century of operation, ion propulsion can't approach necessary speeds for interstellar travel. Nuclear thermal rockets could theoretically accelerate a spacecraft to approximately 100,000 miles per hour. Journey time to Proxima at this speed drops to approximately 28,000 years. Still impossibly long, but progress technically. Solar sails exploit radiation pressure from sunlight to accelerate without carrying fuel. A solar sail might reach 500,000 miles per hour. At that speed, the journey to the nearest star still requires over 5,000 years. You'd cover about 0.6 light-years in a human lifetime, dying in the void between stars. This is the devastating reality. The fastest speeds achievable through any mechanism humanity has demonstrated cannot carry a human beyond our immediate cosmic neighborhood within their natural lifespan. Many 20th century physicists concluded that the universe had imposed cosmic quarantine, trapping intelligent species through simple distance. But they were wrong. Let's tell you why. Einstein's beautiful loophole. In 1905, a 26-year-old patent clerk in Bern, Switzerland, submitted a paper that would demolish everything we thought we understood about time. Albert Einstein began with a simple premise. The speed of light in a vacuum remains constant for all observers, regardless of how fast those observers are moving. Whether you stand still on Earth or race through space at half-light speed, you always measure light traveling at exactly 186,282 miles per second. From this single premise, Einstein derived consequences that shattered human intuition. If light speed must remain constant for all observers, then something else has to give. That something turned out to be time itself. Clocks aboard moving vessels tick slower than identical clocks remaining stationary. Time dilation seemed absurd when first proposed. How could time flow at different rates depending on how fast you moved? But the mathematics proved inescapable, and experiments confirmed it. Time dilation is real, measurable, and transforms everything about the limits of human exploration. The relationship follows a precise formula. Einstein introduced gamma, the Lorentz factor. This number tells you exactly how much time slows down at any velocity. At everyday velocities, gamma barely differs from 1. Your morning commute isn't making you younger in any meaningful way. The magic begins when velocity climbs towards substantial fractions of light speed. At 50% of light speed, gamma reaches 1.15. Time aboard the spacecraft passes about 15% slower than time on Earth. At 90% of light speed, gamma jumps to 2.29. Time passes less than half as fast for the traveler. At 99% of light speed, gamma reaches 7.09. 1 year aboard your ship equals more than 7 years on Earth. At 99.9%, gamma hits 22.4. At 99.99%, gamma reaches 70.7. A single year of your subjective time corresponds to more than 70 years passing on Earth. This is the loophole. The barrier that seems to trap humanity doesn't apply equally to everyone. For a traveler approaching light speed, time itself compresses. Distances requiring thousands of years of Earth time can be experienced as mere decades from the traveler's perspective. Get close enough to light speed, and you could cross the entire observable universe in what feels like a single human lifetime. But here's the cruel twist. The time you save belongs only to you. Everyone else pays the full price. Your friends, your family, everyone you've ever known will be gone long before you reach your destination. Calculations that shatter everything. Let's make this concrete with actual numbers, because the abstract concept of time dilation is one thing, but seeing what it really means for human experience hits differently. Say you want to visit Proxima Centauri, that nearest stellar neighbor sitting 4.24 light-years away. You climb aboard a spacecraft capable of traveling at 90% of light speed. Your gamma factor is 2.29, remember. From Earth's perspective, the journey takes 4.71 years each way, accounting for the fact you're going 90% of light speed, not 100%. Round trip, that's 9.42 years of Earth time. But aboard your ship, time runs slower by that gamma factor. Your subjective experience of the journey is 4.71 divided by 2.29, which equals about 2.06 years each way. Round trip takes you about 4.12 years of your personal time. You leave Earth at age 30, visit Proxima Centauri, and return home at age 34. Not bad, right? You've crossed 8.5 light years and aged only 4 years. But here's what you find when you get back. Earth has aged 9.42 years. You left in 2030, you return in 2039. Your 25-year-old sibling is now 34. Your parents are nearly a decade older. Your friends have moved on with their lives, had kids, changed careers, possibly gotten divorced. That girlfriend you left behind, she's married to someone else now. Your dog is definitely dead. Now let's go farther. The center of our Milky Way galaxy sits 26,000 light-years away. At 99.99% of light speed with a gamma of 70.7, the journey takes 26,000 years from Earth's perspective. But from yours, it takes only 368 years. Still longer than a human lifetime, but we're getting somewhere. Push closer to light speed. At 99.9999%, gamma reaches 707. That same journey to the galactic center takes only 36.8 years of your subjective time. You could make the trip, spend a decade exploring, and return home having aged about 83 years. From your perspective, you've lived a full human lifetime. From Earth's perspective, 52,000 years have passed. Human civilization as you knew it is gone. The Andromeda Galaxy sits 2.5 million light-years away. At 99.9999% of light speed, the journey takes about 3,500 years of your subjective time. Too long for one lifetime. But push this, and the journey compresses to 350 years. Still too long. At this speed, it's 35 years. You could reach another galaxy in a single human lifetime. Theoretically, there's no limit. Get close enough to light speed, and you could reach the edge of the observable universe in decades of subjective time. The entire cosmos becomes accessible to a single human life, at least in principle, the engineering nightmare. But here's where theory meets the brick wall of reality. Achieving these velocities requires energy that makes our current capabilities look like striking matches in a hurricane. The kinetic energy of an object increases with the square of velocity in classical physics, but at relativistic speeds, the relationship becomes far worse. As you approach light speed, your effective mass increases toward infinity. Accelerating requires exponentially more energy for each additional fraction of light speed. To accelerate a 1,000 kilogram probe to 90% of light speed requires energy equivalent to about 1,000 megatons of TNT. That's roughly 20 times the most powerful nuclear weapon ever tested. To reach 99.99% requires orders of magnitude more. The energy requirements become comparable to the total energy output of our entire civilization over years or decades. Proposed propulsion systems that might theoretically work include antimatter rockets, which would be incredibly efficient but require antimatter. We don't know how to produce or store in useful quantities. Fusion drives might work, but require sustained fusion reactions we haven't mastered yet. Laser sail arrays could potentially accelerate lightweight probes by beaming energy from stationary platforms, but scaling this to human-carrying vessels presents enormous challenges. Then there's the deceleration problem. Getting up to speed is only half the battle. You need equal energy to slow down at your destination, unless you're okay with shooting past at relativistic velocities, which defeats the purpose. And at these speeds, hitting a dust particle releases energy equivalent to a bomb. Space isn't perfectly empty. Radiation shielding becomes critical, as even cosmic background radiation blue shifts into deadly gamma rays from your perspective. The human body presents its own challenges. Sustained acceleration must remain below levels that damage organs and bone structure. Life support systems must function flawlessly for decades. The psychological effects of isolation and the knowledge that everyone you knew is aging or dying while you travel would be immense. So how far could a human actually travel in one lifetime? The answer exists in two realities. Theoretically, given technology that could accelerate you close enough to light speed, you could reach galaxies millions of light years away while aging only decades. The mathematics are clear. Time dilation is real. Einstein's loophole genuinely exists. Practically, we remain bound to our solar neighborhood. The engineering challenges are staggering. The energy requirements exceed our current capabilities by orders of magnitude. We don't have propulsion systems that can achieve necessary velocities. We don't have life support for decades-long journeys. We don't have solutions for radiation shielding or navigation at relativistic speeds. The universe has provided the solution. We simply haven't built the key yet, but the door is there, waiting. The cosmic prison isn't sealed, it's just locked, and we're still figuring out the combination. The question isn't whether humans could theoretically travel vast distances in a single lifetime. The question is whether we'll develop the technology to actually do it before we destroy ourselves or lose interest in looking up at the stars. So knowing all this, how far do you really think a human could travel into space before the body finally gives up? Drop your thoughts in the comments, because the real limit might be far more terrifying than anyone expects.